look at it if your brain was too fried to get it during the class. So there'll be a recording available. I will post the link to YouTube video with this worksheet. Okay. So AS3-9, different forms of energy. We're going to talk about that, and then we're going to use law of conservation of energy to do one problem. That's all we're doing. We're doing notes, figuring this out, and doing one example. That's going to pretty much occupy most of our period today. All right. So far we talked about work. I hope everybody can hear me. I mean, can see me, my worksheet that I've shared. So far we talked about something called work, right? And remember we said that work is related to energy. Now we're going to see, later on we're going to see a deeper connection, but right now we're just going to start by saying that there is something called mechanical energy. It's a general term for there are two types of mechanical energies, kinetic and potential. But mechanical energy is a measure of the ability of an object to do work. We're going to focus and understand kinetic and potential energy. We're going to look at their formulas and we're going to use them to do calculations. And I have posted links to physics classroom in this worksheet. As you can see, this is for kinetic energy. Later on, you'll find another link for potential energy. You can also read this stuff in your own time. All right, let's take the notes. The energy associated with motion of an object is called kinetic energy. So energy associated with motion. Anytime something is moving, it has kinetic energy. If something is stationary, if the speed is 0, then kinetic energy is 0. We're going to use Ke as a shorthand for kinetic energy. K for kinetic, E for energy. So Ke is 0 when something is not moving. So think about if I have a brick in my hand and if I'm holding it up in Earth's gravity. If I release it, it can smash, it can hit. If my foot under it, it can also damage my foot. It can do work, okay? We can make it to do work. We actually do use energy associated with motion as well as energy associated with position to do work. The second type that I'm talking about, where if I hold a brick in my hand at a height, that is called potential energy, energy associated with position. But if I release the brick, that potential energy will start to convert into kinetic energy, because energy cannot be destroyed. The brick is losing potential energy when it's losing height. That will go into kinetic energy. But starting with the kinetic energy, that's the energy associated with motion. The formula for that is Ke equals half mv squared. Let's just label this formula there. Ke is the short for kinetic energy. Again, I will grade, the notes will also receive a grade, and there's a decent chunk of these for this worksheet. So do submit those and do take those notes. So Ke, I'm sorry, not Ke, I meant to put units here. I'm going to put the units in the parentheses. I'll just put it on the side here. The units for Ke are, it's a joule, the same as work, or J. That just says or. Sorry about that. Okay. M, you get joules if mass, M, is in kilograms. The speed V is in meters per second. You have to have these units. It can't be gram, it cannot be centimeter per second or miles per hour. It has to be these to get a joule for kinetic energy. All right, potential energy, on the other hand, that I just mentioned, potential energy is the type of energy that a stationary object can also have, this type of energy. Stationary objects can have something called potential energy. If an object is stationary at some position in a gravitational field, like above the ground, then it has potential energy associated with it relative to the ground. That's not the only form of potential energy. But first, let's write this down. Potential energy is the stored energy associated with the position. Let me show you an example that some of you may have seen on at least on television. I don't know if any of you have ever seen a dam, a water dam. So here are some images. One famous one in the United States is the Hoover Dam. You can visit these places. They're pretty awesome actually to visit. I haven't visited one in the United States. A long time ago when I was really young, I visited one in Pakistan, and I remember it is pretty overwhelming. Like they are quite magnificent. So what happens is that in these dams, water is stored in some sort of a lake, and then it is allowed to drop to this some height. So in that lake, it has potential energy. The water has potential, gravitational potential energy relative to the bottom of this well. See how there's a dam built here to separate the lake and this little valley here, if you want to call it. And you literally give it, you can create an artificial waterfall. You can use a real waterfall for the same purpose as well. But basically, you find these dams where you have hydroelectric power plants. Hydro, water, means water. Electric, obviously, electricity. So the water is used to generate electricity. But in reality, what's actually going on, you're using the gravitational potential energy stored in water. You let the water fall there are turbines down here. A turbine is basically sort of similar to a motor, like the type of motors that you have in cars and drills. If you actually take a motor, like if you have some old motor laying around, you connect it up to a little light bulb and you actually start cranking it, it'll basically be a generator. So any motor that you can take and you literally just crank it by hand and you connect up a circuit to it, you can actually use it. A generator is basically a motor working in reverse. Okay. So these turbines that I'm talking about are basically, they're part of generators. Okay. So there are generators down there that you run by letting the water fall. It's kind of like a water mill. It's like a really advanced water mill. Okay. And that can be used to generate electricity. All right. Now, nuclear power plants are quite different. In nuclear power plants, the principle is the same. You use nuclear energy, and again, that's another form of potential energy. There is potential energy stored in the tiniest part of the atom, which is a nucleus. And then in that nucleus, if you unleash that potential energy, it's called nuclear potential energy. You can cause destruction or you can create energy. You can do good things, bad things. It's up to you, but you can generate a lot of energy. So with the nuclear reaction, with the nuclear power plants, you can actually, what they do is they use all that energy to generate steam. And then steam in turn can run turbines, the same sort of turbine that we have in a hydroelectric power plant, and that generates electricity. And again, like I said, the turbines are kind of like a motor working in reverse, to put it simply. So it's really, really interesting stuff how all these different sources of energy and different forms of energy are related. But if you're interested in nuclear energy, for example, unfortunately, we won't have time or we don't go into nuclear physics. There's a really actually good movie. I don't know if you've seen that or not. It's called Chernobyl. It's HBO mini. I think it's an HBO series. If I can spell it right, I'll show you. Chernobyl series. There we go. It's an HBO series, Chernobyl. It's about the Chernobyl disaster that occurred happened in Russia in a nuclear power plant. It is really good, by the way. I mean, it's the type of movie where I was literally like sitting on the edge of my seat throughout the series with my jaw dropped throughout. I mean, you watch it and you can't even believe that this actually happened in the real world. It sounds like out of some dystopian sci-fi, not dystopian, but out of some sci-fi movie where something has gone horribly wrong. But yeah, it happened in the real world. But now, of course, there are a lot of safety. We take a lot of precautions and stuff now with the nuclear reactors, but bad things can happen. But give it a chance since the winter break is coming up. Has anybody seen this? I'm just kind of curious. Did anybody watch it? Well, there you go. If nuclear,
I mean, I haven't watched it, but I know about the event itself.
yeah, so check this out. You might
Good old
actually,
elephant
this is actually
story.
pretty good and pretty accurate too. And this is more than just about the nuclear disaster. It's about the handling of the whole situation, the politics of it, um, and why freedom is so important. And it's just, there's so many components to it, but do give it a shot. All right, back to our worksheet. So that was an example, the nuclear potential energy. There are different forms of potential energy. But we are going to focus for calculation purposes on gravitational potential energy, like the one that I showed you in the case of a dam. Okay. All right. And there's also another type of potential energy called elastic potential energy. By right now, you should be seeing my worksheet, by the way, on the, I just shared that. I hope that's what you're looking at.
Dr. Naeem, could you scroll up a little bit?
Hmm? Oh, you want to see this stuff? All right.
Yeah, thank you.
All right. If you take a rubber band and you stretch it and you use it as a catapult, the stretched rubber band also has energy associated with it. It's called elastic potential energy. So that's another form of potential energy. And you can do useful work with that. All right. Can I move up? So let's fill this out. This last blank here says the energy stored in an object raised at a height can do work that is the gravitational, like in a water dam. All right. So for the gravitational potential energy, the formula is this. We use PE as a shorthand for potential energy. So if I raise some brick at a height, the brick has a mass. The more mass the brick has, the more potential energy it has. It also depends on how strong the gravity is. So it also depends on G. And it also depends on the height. So I can use a brick, just like with water. All I need is imagination on how to make it do some work. So that's the formula for potential energy. M again is the mass in kilograms. G is 9.8 meters per second square. And H is the height in meters. And PE, just to remind you, is potential energy. Or sometimes GPE is written for gravitational potential energy to be more specific. But we're just going to use P's just because we're not going to use other forms in our calculation. And this is in joules again. So I put all the units in the parentheses there. So in all the problems we're going to be concerned with, we're going to look at kinetic and potential energy. And the sum of those is called the total mechanical energy, or sometimes just mechanical energy. The shorthand for that is ME. So ME, basically this formula is this. ME is KE plus PE. And we might even add, later on we'll see, we might add heat to that as well in the problem. But right now we're going to concern with no heat being generated. The law of conservation of energy tells us that this total mechanical energy remains constant provided no external force acts. So what do I mean by that? By external force, I mean nothing is pumping energy into the system or taking it away. Friction and air resistance can remove energy from a system, right? Because heat is generated. Heat can just literally, if you want to use the loose term, fly away. It's going to, the heat is removed. Heat can carry energy away from the system. So the total mechanical energy will not be constant in that case. So for the total mechanical energy to be conserved, the condition is that it should be an isolated system. It should be isolated from its surroundings. There should be no outside forces, external forces acting. So a force is called an external force if it can change the total energy. If it can change the total energy, the total mechanical energy of a body, Example, air resistance, friction. Applied force can also be one. Like if you start pushing on a box, you're going to change its total energy, right? You can accelerate it. So applied force, all sorts of any force can be an external force, by the way. But it depends on the situation. Like you have to understand what it means. Because in the problem where I raise a brick and I drop it, there is a force acting. It's gravity, but gravity is not external force. Gravity is an internal force. Because gravity is built into the formula for P. See this potential energy? If I raise a brick above the ground, if this happened in outer space where there was no gravity, the brick is not going to have any potential energy. So gravity is part of the equation. It's internal. So that's not external force. So that brings us to this next thing. What's an internal force? A force is called an internal force if it cannot change, if it cannot or does not or whatever, change the total mechanical energy of a body. Examples are gravity. And depends on the problem. We're just going to restrict ourselves to gravity. But you can have spring forces and some sort of an internal force, which is part of your potential energy in the equation. Like if a rubber band is doing the work and that is providing the potential energy, then that's an internal force. And the total energy will remain constant. All right. So I mentioned this in words that a brick drop from a height, its gravitational potential energy decreases, but its kinetic energy increases such that the total mechanical energy remains constant. We say that potential energy has transformed into kinetic energy. Now we're going to do that example. Any questions before I move on? Is everybody clear about internal versus external energy? All right, now let's apply all this. I'm going to write down these two formulas up here that we have. VFKE is half mv squared. PE is mgh. And then we know that the total mechanical energy, ME, is KE plus PE. We're going to use all of that, and we're going to solve this problem. This is kind of like a table here. This pertains to this roller coaster track. So what you're seeing in this diagram is a roller coaster track. A roller coaster car is released from here, and it is at the mercy of gravity. Gravity is the only force acting on it, so it's an internal force. There's no friction in this problem, so there's no external force. It's going to actually start sliding down. It's going to lose height as it slides down. So it's going to lose potential energy, and then the potential energy energy cannot be destroyed. It has to go somewhere. It's going to convert into kinetic energy. So basically, this car is going to gain speed as it slides down. Then it's going to go around this loop and then go here and then basically like that. There are 4 positions of interest. 1, 2, 3, 4. We're going to do calculations of PE, KE, ME, and V for each position using this info. So ready? All right. At position 1, let's calculate PE at position 1. So see how the height is given? So pay attention because I'm going to ask you to do some calculations in a minute. I'm going to do this one step for you. You're going to answer a few other questions. All right. So at this height, it's released from rest. Let's calculate the potential energy. Actually, I'm going to use this space to do the calculation. At the position 1, PE is, remember the formula is mgh. G is always 9.8. M is 50, it's given here. So 50 times 9.8 times the height is 4. That gives us 1,960 joules. So let's fill that out. 1,960 joules. I'm going to not write joules here. It's just, I'll be cramming too much stuff in there. All right, my first question to you all. What's the kinetic energy of this car at position 1 if it's released at that point? To chat, if you could tell me what's the kinetic energy. All right. Look at the formula for help or your understanding. Yep, so far correct. Both of you who sent the answer. So what is the kinetic energy at position 1 where the car is released from rest? All right, folks, what about the rest of you? Let's quickly get it moving. This answer shouldn't take too long. If you're not sure, then let me know because I need to hear something from you. Ben, yours is correct. The rest of you need to think. I don't know where you got those numbers, but look at the formula for kinetic energy. Kinetic energy is half mv squared. And I'm saying at position 1, the object is released from rest. Brandon, that's correct. Released from rest, half mv squared. You can change your answer as well, by the way, those of you who got it wrong. Okay, so I just said V is 0 up here. V is 0 at rest. It's released from rest. So shouldn't Ke be 0? Something that is not moving has no kinetic energy. V is 0, half mv squared, that will make it 0. What about the mechanical energy? That one we'll just do it together. Mechanical energy is the sum of Ke and Pe. You add those two and you get 1,960. Law of conservation of energy tells us that if there's no external force acting on a system, there isn't one, there's no friction or air resistance here that we're told about, then the total ME should be the same. So at all the different positions, ME is going to be exactly the same, the total of the two. But each energy can change, right? K can convert into P and P can convert into K depending on which height we're at. Ask me if you have any questions at this point, because I'm about to ask you to do the next few through chat. All right, let's look at position 2. Position 2 is 3 meters above the ground. Using just that information, we're going to calculate PE, KE, and speed. So let's start with PE. Can you guys tell me, by doing a calculation, what PE at height 2 is going to be? All right, so I'm going to give you no more than a minute for that. This time, I do expect to hear from all of you. If you're not sure, just tell me, because this way it'll help me gauge like how many of you are stuck or what's going on. Sam, Garrett, Trey, Isaiah, correct. Oh, Sam, sorry. Sam, you gotta try that one again. I don't know why I said your name there. Try that one again, Sam. But the rest of you, yes. Will, yes. Ben, yes. Again, folks, those of you who haven't answered it yet, potential energy is mg8. Mass is 50, g is 9.8. The height is also given 3. All you really got to do is multiply those 3, right? That's how you get it. So let's write that down. I'm going to keep moving. Potential energy is mgh, which is 50 times, I have those formulas at the top. Let me see if I can make them visible. There we go. There's the potential energy formula. M times G times H, and that is 14, what did we say, 1470. Oops. 1470 joules. So let's put that in our table. Now the more interesting question. Let's see who gets this one. Okay, potential energy is 1,470 joules. The total mechanical energy is 1,960. What is the kinetic energy at position? Kind of curious who gets this one. All right, let's see. So now the question is, what is the kinetic energy? You have the information, the total of the two is that. Ben, correct? Anyone else? Samuel Vance, yes. Will, yes. John, yes. Garrett, yes. Sam Smithers, yes. Trey, yes. So Isaiah, think about it. Do you think the card is not moving at that position too? Cash, yes. If you're in a roller coaster like this, and if this car stopped moving, do you know what's going to happen? Do you want to answer that? I mean, unless if you were like, usually these cars are kind of locked, all right? But if there wasn't a locking mechanism, if this is some sort of usually they are always locked. But if it stopped moving, it could actually fall down as well. Sometimes you can have a roller coaster where I'll show you one I have in class. Yeah, if it wasn't locked, which most of these are, all of these are actually, they wouldn't leave it at the mercy of, if the friction was too high and the cars slow down, you would literally just fall down. So obviously they wouldn't have it like that. All right, let's discuss it together. The total energy is 1,960. Out of that, potential energy this time is 1,470. At position one, all that total energy was potential energy, but now only 1,470 is potential. What happened to the rest? Energy cannot be destroyed. So it transformed into KE. So how do we find that? By simply taking the difference between the two. So KE would be 1,960 minus 1,470, which is 490 joules. Right? So we've got KE. The next challenge, if you have KE and you have the formula for KE, maybe we'll just do this one together. Can we find how fast this car is moving at that position? So I'm going to free up some space to do that. So at that position 2, we have KE. We are interested in calculating the speed now. Only this formula has the speed. We already know the KE, which is 490, is a half. M is 50 times V squared. So let me show you the algebra. Some students get confused, so make sure you pay attention to the algebra. So first, I'm going to multiply 50 times a half, which is 25, and I'm going to flip the equation. 25V squared equals 490. Then I'm going to divide both sides by 25. And then I'm going to, let's see what's going to be next. So V squared is 490 divided by 25. Does anyone know how to get rid of a square there? We need V, not V squared. Anyone wants to say it out loud? How do I get rid of that square?
Square root.
Yes, thank you. Square root basically cancels that square. Whatever we do on one side of the equation in algebra, you always do the exact same operation on the other side. So try this on your calculator. Do try it because you don't want to find out during a test that you didn't know how to actually do that on your own. It should be 4.4 meters per second. So based on that kinetic energy and mass, this is how fast it's moving. Let me shrink this a little. Any questions? All right. One other thing I didn't mention was, see the potential energy at position 2. There's another way you can find it. Potential energy is proportional to height, right? The height doesn't appear as square or anything. So potential energy, this is at 3 meters, this is at 4. You know that the height at 4 meters, it's not 1,960. At 3 meters, it's going to be 3/4 of the original potential energy. So if you just took 3/4 of 1960, you would get the potential energy of 1,470. That's another way of getting that. I'm a little hesitant in mentioning it because sometimes students try to do that with speed as well. Like if you're finding the speed and you know the speed in another position, it does not work for the speed, because speed appears as v square in those formulas. So be careful, okay? Only for potential energy you can do that, because potential energy is proportional to height, not height square, not height cubed or anything. Okay. So if height doubles, potential energy doubles. If height goes down and becomes 3/4 of the original, then the potential energy becomes 3/4 of the original. All right, now the next one, I'm going to have you do all the parts one at a time through chat. Now we're at position 3, ground level. Height is 0. What is the potential energy at position 3? Through chat. PE at position 3. What is that? All right, let's see. Yes, Trey. Sam, yes. Ben, yes. Sam Smithers, yes. Will, yes. You got the idea, right? Seems like everybody's rolling along here. If there is no height, if height is 0, then relative to that position, the potential energy is 0 because it's mgh. So let's put a 0 there. All right, next one. What's the kinetic energy at position 3? And let me tell you, it's not 0. The car is moving. Actually, the car is going to have the fastest speed on the track is going to be at 3. The greatest thrill is going to be at 2 probably, but because you're upside down. But all right, let's see what you got for KE. Samuel Vance, yes. Garrett, yes. Ben, yes. Trey, yes. Yep. Sam, yes. Good. You guys are rolling. You're all getting it. Awesome. Everybody got it so far. So basically what you realized was, now it's the ground level, there's no potential energy. So all that total ME is now KE. All that total energy is now in kinetic energy. So KE is 1,960. So when you add the 2, you get that ME. Now, can you all do the calculation for speed for me? Have your calculators ready and calculate the speed for me. I'm going to give you about a minute. Let's see what you get. Wow, some of you already got it. Ben, yes. Samuel Vance, yes. Trey, yes. Garrett, yes. Pretty good. For the last period, you guys are rolling. That's good. Uh-oh, calculator died. Yeah, that's too much for a human calculator, maybe. All right. Anyone else got it? As you do this, I'm going to start doing this here. Pretty much like what we did here, except in this part, you're changing your KE to 1960. And then you're going to solve for V, which basically means, I'm just going to skip to the very last step. It'll be 1960 divided by 25. You take the square root, which is 8.9, just like the previous step, except the kinetic energy is different. And look, you can check your answer, roughly get an idea if you're on the right track, because this is faster than it was at that height, which was 4.4. This was 4.4, and this is 8.9 meters per second, of course. It's hard to squeeze all this stuff. All right, I'll tell you what, I want to stop at this point. I am going to grade number 4 for you. And 4, there's a little difference. You're given the speed, you're given this H6. You're going to give me potential energy and Kinetic and, oh, I'm sorry, I made a mistake there. That's not speed there. That's the height. Speed is given. It's not written on the table. Speed is given. You're going to calculate PE, KE, and height. And I will grade that for accuracy. Tomorrow, I'm going to give you time to finish this. Don't worry about a homework tonight. Just take it easy if you're caught up. Tomorrow, we're going to do this and a concept builder. So I'm going to stop at this point. I think our brains are probably, my throat is fried, and I'm sure your brains are fried. So let's stop. Zooming can be a little rough. All right, so I'm going to let you guys go. Have a nice day. I'm going to post this video link within the next few minutes with this worksheet.
Miss Naeem,
Uh-huh.
hang on one sec. If we don't have school tomorrow, or if we're out of school tomorrow, what should we do about making up my test? Should I just take it after class tomorrow at home? Because it's looking like we're storm later today.
So you're gonna take it next week then.
Okay.
So all the students, yeah, who are supposed to take the makeups at school will take it next week. So when do you come in now? Next week? Hey, hold on one second.
Yeah. If we don't have school tomorrow.